Thank you for coming. My name is Emma. I'm a developer advocate for Google Cloud Platform. Today's topic is the Sandboxed container runtime environment, gVisor. So I think everybody uses containers here, right? Containers are great. Docker was released in 2013, but containers were used before that, even there was no Docker. But the technology has really taken off since the release of Docker. Docker Inc. reports that there have been more than 29 billion downloads of containers from their website. And Google also has used containers to manage their applications for more than a decade. So containers and Docker are two separate technology or terms. Containers has been around for more than a decade, while Docker is a fairly new technology. Google uses containers, and it launches over 4 billion containers per week. And people like containers because it's really fast, and it provides better isolation than regular processes, and it provides consistent environments for multiple host OS and hardware. So if you package your application into a container, you can use it and deploy it to different environments and different host operating systems without worrying about compatibility too much. But containers do not contain, and there are security concerns around. Dan Walsh, a developer at Red Hat, said containers do not contain in 2014. And there have been a lot of efforts and mechanisms to try to isolate containers and applications from host operating systems and other containers, such as users, namespaces, Cgroups, capabilities, chroot, seccomp Linux security modules. I'll explain individual mechanisms later, but despite these efforts, these concerns remain true, unfortunately. So in order to better understand the current situation, let's take a little bit back in history and how we invented different mechanisms to provide better isolation and security to containers. Once upon a time, this is roughly 20, 30 years ago, I think, every service ran as root. So instead of using separate unprivileged users such as FTP, SSH, HTTP, everything would run as root. So of course, these services could access all of the files and resources, as well as devices. And of course, as root, it could reconfigure network devices so that network configurations are vulnerable from these services, are modifiable from these services. And of course, as root, it can perform any kernel system calls and kill or send any signals to any processes. So in a perfect world where everybody makes no mistakes, it could be fine, but the reality is different. Anything could go wrong. That could be a bug in software, like a small error in a script, like RF, undefined value, asterisk could mean like RF asterisk, like it could delete everything in a directory, or some malicious activities could be fatal, and a single vulnerability could mean total exploit of the host, total exposure to the host. So people decided to run services as unprivileged users, as we do these days. For example, you run FTP servers. We don't use FTPs as much as we did, but we run these services as different users so that when permissions are properly set up, they have limited access to device and network configurations, as well as file systems. And these permissions were checked by the kernel before execution, and other system calls are also checked by the kernel. And it also limits the ability of processes to send signals to other users' processes so that they can't simply kill or terminate processes of other services. But certainly this is not enough. What if the process can set UID so that it can pretend as other users or use row sockets? Row sockets is a tool to create any packet they wish. So it can generate any packet that not necessarily valid or appropriate for the given process. So we take care of capabilities. Docker, for example, drops a lot of capabilities of containers like sysadmin, sysnice, netadmin, sysrow.io, sysmodule, etc. Like sysadmin or netadmin, they sound really privileged, right? These capabilities define certain methods and certain system calls that a process can perform. And fewer capabilities mean better isolation because it limits what a process can do under these capabilities. So Docker and other container engines limit capabilities of container processes, so they have limited access to system operations. But this is not enough yet. We haven't talked about resource isolations. For example, even with limited capabilities and running as an unprivileged user, a process can consume a lot of memory, or by forking, it can consume a lot of memory. And these processes can also use a lot of CPU, and this is not exactly what we want, usually. So Cgroups came into the Linux kernel to limit account and isolate resource groups. So the idea of Cgroups is to make a group of processes and control the amount of resources that these groups can consume. These resources include CPU, memory, devices, and CPU nodes and memory nodes. For example, you can set a group of processes consume up to 50% of the entire processors of memory. So this is quite useful when you want to make sure that different group of processes share this exact same amount of system resources. But processes can still see all users' processes, network interfaces, mount points, this means file systems in the system. For example, any process in the system can still get a list of all the processes running in the system. So we put namespaces for name isolation. This name isolation is not really a good name for this feature, but naming is quite difficult in computer science. So this provides isolation for namespaces. There are currently 7 types of namespaces. Network, so network interfaces and addresses. PID, process ID, mount points, user, IPC, UTS. UTS means Unix time sharing, but it really means host names. So different namespaces can have different host names. And Cgroups. So with these namespaces, containers can have their own network interface or process space. For example, PID1 or PID0 can mean different processes in each of the containers. Or, for example, in terms of file system, if you want to use /app for your application, you don't have to worry about other applications using the same path. This not only provides great isolation between containers, but also provides great flexibility. These different containers don't conflict with each other. So now a process is contained, or do containers contain? Still, containers don't contain, unfortunately. So this is a list of past vulnerabilities that caused these isolations breaking. For example, dirty car is an exploit that uses race condition to break these isolation. And Spectrum and Meltdown use speculative execution of the CPU and try to get kernel memory and other protected memory from an unprivileged process. So with this, a single vulnerability in the kernel or any of the system components could lead to privilege escalations or unwanted information leaks. And this is not ideal. And also, network stack is shared across different containers. So for example, in 2013, there was a vulnerability that a single malformed packet, a remote packet, can crash a host kernel. So if any of the applications receive a malformed packet, that could terminate the entire host operating system. But why, despite all of these efforts, containers are still prone to these vulnerabilities. That is because regular or normal containers share the same host operating system, the same kernel and device drivers. So hardware and a lot of system resources are exposed to the applications. They share a large attack surface between applications kernel. So any vulnerability or any error could mean a direct exposure of the other kernel memory structure or memory data or other application to a malicious process. So when thinking of making containers secure, these are things we want to keep in mind. Any programs in containers should not be able to exploit host. So this is the idea. And a containerized process can do anything inside a container, but they shouldn't affect anything else. But when security is complicated and difficult, nobody would use it. So it should be as easy as normal containers. Like no application modification would be required, or you don't have to configure anything like policies or rules or complicated configuration files to use these security methods. And also, you want to keep the existing good aspects of containers, the reasons why you like containers. These include flexibility and small footprint. You use containers because they consume less memory and they are fast. And these processes start fast, so we don't want to slow them down. So gVisor was designed these limitations and these issues in mind, and it is different from other methods of privilege separation. One of the existing technologies is virtual machines. So virtual machines provide a great level of isolation between applications and the host kernel. Virtual machines are essentially an emulation, hardware emulation to run a full operating system. So instead of running applications directly on top of the host kernel, virtual machines provide a virtual hardware interface to guest operating system, and then an application runs on top of the guest operating system. So in order to reach to the host kernel, these applications must first get to the guest kernel and then break the isolation of the VMM or hypervisor and then somehow find an exploit in the host kernel, and then get to the hardware or other processes. This is really, really hard. And you need to have exploitable vulnerabilities in multiple points at the same time. And cons are high overhead. Of course, you emulate a hardware interface. So this is slower than simply running a process. And of course, a full operating system means more memory. And since this provides hardware instead of system, like instead of containers, it's really hard to change configurations of hardware on the fly, such as increasing or decreasing number of cores, or like adding or removing memory during the execution without rebooting or without changing, causing disruptions. And another technique is rule-based access control, such as seccomp, SE Linux, AppArmor, etc. So these are implemented within the Linux kernel, and so that they provide close to native application performance. So they are very transparent to applications. So the performance is really fast. There is virtually no overhead. So this is really good when it works. It's really hard to define policies and rules for these systems. So you need to know exactly what system calls and what system resources your application would need during the entire life cycle of your execution. For example, in the case of HTTP servers, you need to know what kind of system calls they need and which files and which system ports and other resources they need during their execution. This is extremely hard. So a lot of documentations and manuals of software tools say disable SE Linux before installing, actually. So, and the biggest biggest issue of these solutions is you can't define a policy for unknown binaries that you don't know yet, such as user-uploaded binaries or new kind of software. Because you can't get a list of system resources of binaries or applications that you don't know. You can't simply predict these resources. So in order to make containers secure, we want the best of both worlds. So the good thing with virtualization is all of the processes have independent kernels, and they have full guest operating systems. So it's really hard to get to other operating systems or other processes. And hardware virtualization. Virtualization is a good way to provide additional layers of defense. It's simply hard to break these layers to get to the host operating system. And modern processors provide hardware virtualization that guarantees clear privilege separation and encapsulation of different processes, like guest operating systems and host operating systems. So these are strong guarantees provided the hardware. So relying on these mechanisms is really a good idea. But the bad things with these is, so again, virtualized hardware interface is very inflexible. You can't change number of cores, CPU cores, or the amount of memory during execution. And running multiple copies of Linux kernel is not a particularly good idea because they're too big. And not only the memory consumption, but the software itself is really big. Linux, the latest Linux provides 319 system cores for x86-64 architecture. This is a lot of system cores. And recently, Linux achieved a milestone of 20 million lines of code. So this is a significant amount of code. It's extremely hard to make this gigantic software secure. There could be a lot of security and non-security related issues. And yes, since 1999, there have been more than 2,000 vulnerabilities found in Linux. And 259 of them were actually privileged escalations. So any of these vulnerabilities could mean escalations from unprivileged users and to privileged users, as well as break escalations or breaks of any of the isolation mechanisms that we discussed before in this talk. So instead of using virtualization, we thought of different mechanisms to provide better isolation. One of the techniques is sandboxing. Sandboxing is fairly proven and effective means to reduce attack surface. It is used by JVM, the Java Virtual Machine, or web browsers. So when you run a JavaScript, they don't have access to the host running the browser. They run in a sandbox environment, so it has limited access to predefined resources. So when you run a script, it doesn't have access to your files on your hard drive. It instead has access to a list of interfaces defined by the JavaScript standard or browser standard. So we could do the same for Linux processes. If we provided a sandbox, an attacker can't escape, first needs to escape from the sandbox in order to get to other processes or the kernel itself. So gVisor is exactly the sandbox that works on top of a host operating system. It is a user mode mini kernel, so it works independently from the host Linux kernel. And when application performs system calls, gVisor traps these system calls and execute them inside the kernel, inside the gVisor mini kernel. So from the host kernel perspective, gVisor is just a normal process. So thread and memory allocation is as flexible as other regular processes. And gVisor doesn't implement all of the system calls. So it's significantly smaller than the the actual Linux kernel. And instead of providing the hardware virtualization layer, it provides a thin layer of system calls. So it has lower overhead compared to other hardware virtualization hypervisors. So gVisor provides an environment to run untrusted applications in a sandboxed environment. It currently implements 211 system calls. So it's roughly 2/3 of the entire system calls of the current Linux provides. It's not 100%, but this is usually enough for many of the applications. This is not filtering. It executes most of the these system calls inside gVisor. And this is not a port of the Linux kernel. This is a re-implementation in a user mode. So this is quite different from user mode Linux. And unlike Knuckle and other sandbox technologies, gVisor is able to run unmodified Linux binaries. So you can run your existing containers inside of gVisor as they are. And gVisor is designed as secure by default, so you don't have to configure filters or policies rules as you'd have to with AppArmor or SE Linux. And as we discussed in virtualization, gVisor provides separate kernels, separate mini kernels for each of the sandboxes. So even if someone compromises one of the kernels, they still have to get to other kernels to affect other processes. And it's written in Go for memory and type safety. There are other languages that provide the same kind of guarantee, but we chose Go for performance, memory, and type safety. Let's take a closer look inside gVisor. So gVisor is actually two separate processes inside. The left side is Sentry, and on the right side is Gofer. Sentry is the mini kernel that is written in Go. So Sentry traps system calls from these applications and emulates these system calls. So instead of passing through to the kernel, it processes most of the system calls inside, and when necessary, it passes to the host kernel. And between Sentry and the host kernel, we use seccomp to reduce the attack surface, and it defines exactly what system calls it needs to execute gVisor or Sentry. And Gofer on the right side processes file accesses, and they communicate in IPC. So whenever Sentry needs to access a file, Sentry instead sends a request to Gofer, and Gofer processes these access requests and returns them to Sentry. And network is also handled inside Sentry. Sentry has a user mode network stack written in Go. So instead of using the shared kernel network stack, everything is processed in Sentry. So why do we have two processes instead of one? That is because some of the sensitive operations are socket and open. So these are two most exploited system calls in Linux. These are really easy because these system calls try to access to new resources. So they provide large attack surfaces to applications. So in order to limit attack surface here, Sentry is not allowed to perform these system calls. These are controlled by seccomp for Sentry. So whenever Sentry needs to access system resources, sockets, or files, Gofer instead performs these actions. So even if Sentry gets compromised, it can't open a new file. It can't write directly to other files in the system. It then needs to compromise other processes or Gofer in order to write to or read to other system files or system resources. And when trapping system calls, gVisor uses two different mechanisms independently implemented. One is ptrace. Ptrace is a debugging interface provided by Linux kernel. Ptrace system EMU is used to trap system calls. So whenever user application issues a system call request, then the process, the execution is stopped, and Sentry resumes the execution whenever these system calls are handled inside Sentry. ptrace works with all of the Linux operating systems. It doesn't require special hardware support. And the other mechanism is KVM. KVM is originally developed for virtualization, but it can be used to provide a separation between host operating system and containers. So gVisor can use KVM. And in this case, gVisor serves as a hypervisor and guest OS. So it's a mini kernel, and it also serves as a VMM from the KVM perspective. But in the case of KVM, hardware virtualization is required, so it doesn't run on any hardware. But when this support is provided, KVM guarantees certain memory separation and privilege encapsulation. And gVisor is a bit slower than normal containers, honestly, I have to say, but it's still small. It consumes 15 megabytes of memory, and when starting a new process within gVisor, it takes roughly 150 milliseconds. So it's slower, but still fast. And significant overhead incurs when system calls are executed. So if you're processing inside a process or doing work inside a process, it's usually fast. But if your application is system calls heavy, gVisor might not perform optimally. So gVisor is pretty lightweight and good, but it's not perfect either. gVisor is not designed to run different guest operating systems. So you can't run Windows on top of Linux, for example, by gVisor. And gVisor is not designed to run fully trusted binaries. In other words, running your own applications. So your own applications know, when you write your own application, you know what they do. They are not supposed to do malicious activities, usually. So in these cases, gVisor simply incurs additional overhead on top of the containers. So maybe you want to use regular normal containers to achieve optimal performance. And as I said before, system call heavy applications are not ideal for gVisor, but this is not usually the case for most of the applications. And the goal of gVisor is not to provide 100% of compatibility for applications. So that would mean we implemented everything in the mini kernel, right? So it needs to provide the exact set of system calls and system resources inside Sentry. That's not the goal. Of course, the team is trying to provide better compatibility and better support for applications, but the goal is not definitely provide 100% of the system calls. These are the list of tested applications. Tested doesn't mean guaranteed or supported, but I think you can spot some programming or execution application environments such as Java 8, Golang, or PHP, Node, Python, and others. So if you can run these programming environments, that means you can run any programs you'd write on these in these programming languages. And there are other applications like Memcached or MySQL, Mongo, and others are already tested on gVisor. So it provides a pretty good compatibility, but not perfect. And then what is gVisor really for? So this is one of the use cases. Google uses gVisor to provide Google App Engine. So Google App Engine is a PaaS environment where you can upload your source code and then Google takes care of the rest. It scales automatically out and in depending on the workload. So they can't use virtualization or to scale, launch new application, new instances of the software because it takes too much time. So gVisor was designed to provide faster startup and low overhead for these kind of services. So in this case, as long as Node.js works on gVisor, you don't have to implement all the system calls to make your applications work. So this is one of the ideal use cases or valid use cases of gVisor. So this use case is pretty limited to certain users. Not everybody runs cloud services. But I think running these technologies, especially when gVisor is a new way of running containers in a secure sandbox, it's different from virtualizations. It's different from regular containers. It's different from SLinux AppArmor. So learning about these new technologies is, I think, is important to make informed decisions when choosing the right platform for your applications. Because different tech stacks, like virtualization or native bare metal hardware, containers have different pros and cons. So choosing the right platform is extremely important for your applications. Lastly, running gVisor is simple. So when you use Docker, you run Docker run container and arguments. Using gVisor is simply adding --runtime equal run_sc. So this Docker uses gVisor, the secure runtime, instead of the regular Docker runtime. And Kubernetes is all supported, though it is still experimental. All you need to do is to edit the crio.conf configuration file, adding one line to make specify the container runtime is usually sufficient to change the container runtime for the regular Docker to gVisor. Currently, single container pods are supported, and multiple container per pod is planned but not implemented. So wrapping up, gVisor is a new way of running containers in a sandbox. And sandbox is a separated, isolated environment for applications. And gVisor is fast, especially the startup time is very fast compared to other isolation mechanisms. It provides the same flexibility as containers and the regular processes in terms of thread and memory allocation. It incurs minimal overhead except system calls. It's written in Go for memory safety and type safety, so it's pretty safe and secure. And gVisor is intended to provide strict boundary between container and host operating systems so that it's safer to run untrusted binary in containers. You need to have multiple vulnerabilities at the same time to get out of the containers and reach to the host kernel. It's not still impossible to exploit the host kernel, unfortunately, but it's much, much safer than regular containers. And again, knowing about underlying technology is important to make informed decisions when choosing platforms. gVisor is available on GitHub. If you Google gVisor, I think this comes on one of the top in the search results. If you have any questions, feel free to reach out to me on Twitter, or my email address is yury@google.com. gVisor is really easy to try. It usually takes 15 to 20 minutes to build and try the first Hello World example. So go to the URL and please try the software. That's it. Thank you very much.